Sugam Prabha. Digital India. Educated India.
Hello students. So in the previous class, we looked into the canonical forms and also how to identify second order partial differential equations, where we learned how to categorize a given second order PD based on that discriminant, which was s square minus 4RT, based on which we can call a given second order PD either a hyperbolic type, parabolic type, and elliptic type. Now, based on which, I mean, we could also be able to obtain the required canonical forms. So that's what we did in the previous class. Today, I'm going to basically talk to you about these three special cases of PDs, which are this wave equation, heat equation, and Laplace equation. And we will see how they are coming from the from a physical situation and how we are ending up with these equations. If I remember correctly, at the beginning of this course, Professor Ganguly has already given you a motivation towards partial differential equations, where he derived the equations for basically he derived the wave equation, where he used the vibration of a transverse string, and then he derived the equation of this type. I hope del square u by del t square c square times del square u by del x square. You can also take it as a c, and here let's say the length of this string was 0 less than x less than l. So l is the length of this string and t is the time period. And now you can obviously complement this wave equation with several initial condition, with some initial condition or some boundary condition, and then we can be able to solve this wave equation. So I will come to that, but since you already know how to derive the wave equation, I'm not going to derive the wave equation again. What I will do, I will start with the heat equation. All right. And I will also show you how to get the Laplace equation. So this is the wave equation, which you are already aware of. So wave equation. All right. So now, let me start with the heat equation. So heat equation or heat conduction problem. Sometimes we can also call it a heat conduction problem. All right. So to derive the heat conduction equation, first of all, let us consider a homogeneous isotropic solid. Homogeneous basically means that the material distribution on this given solid is uniform. That means it's not like you have some part of the solid present, then you have some hole, then again you have some solid present. So then in that case, the distribution of the material is not uniform. It's not homogeneous. So then you might call it as a heterogeneous material. So people from material science or engineers, they call such materials as heterogeneous material. So we are not dealing with, for the time being, heterogeneous material. In order to derive the heat conduction equation, we will start with homogeneous material. That means the material is uniformly distributed on the solid, basically. So the solid which we are considering, the distribution of that material is always uniform or homogeneous. All right. And let V be any arbitrary volume inside the solid. Bounded by the surface S. So let V be any arbitrary volume inside the solid bounded by the surface S. And let delta V be any arbitrary volume element. Volume element. I'm just quickly going to check whether the screen is shared or not. So yes, it is being shared. So now the heat energy. So basically the heat energy that is stored in delta V is equals to this. We can write very easily C times rho times U times delta V, where our C is the specific heat, of this solid, rho is the density of this solid, and U is the temperature distribution, which is a function of the position and the time. Position and the time t. Position is obviously the space variable. That so if you are considering a three-dimensional geometry, then in that case, u will be a function of x1, x2, x3. If we are considering the coordinate configuration at x1 axis, x2 axis, and x3 axis, and the time t. So u will be a function of x1, x2, x3, and the time variability. And if you consider the coordinate configuration as xyz, then in that case, your temperature distribution u will be a function of xyz and t. All right. So now this c times this c times, so c times rho times u times del v was the heat energy that was stored in the volume element delta v. So therefore, the total heat energy will be given by integrating this small heat energy that is stored in delta V over all the volume V. So we have to integrate. If you want to know how much heat energy is there in the volume V, we just have to integrate this one over the entire volume V. All right. So that is what we are going to do. So therefore, so this is what we are going to do. Therefore, the total energy or total heat energy in V will be volume integral over V C times rho times U times d of V. All right. So this, let us call it as equation number 1. Again, let delta S be a surface element corresponding to delta V. Surface element enclosing the volume, this delta V. Then the heat flow across delta S will be K times gradient of U dot N times delta S, where N is the, where, let's write where N is the outward drawn normal, outward drawn normal to the surface delta S, to the surface S, yeah, to the surface S, and K is the thermal conductivity. K is the thermal conductivity of the solid. Conductivity of the solid. Some people also call it as coefficient of thermal conductivity. In case of diffusion reaction equation, people also call it as coefficient, diffusion coefficient. So it has many names, but basically it signifies some kind of property that is associated with the solid or the kind of medium that we are working with. All right. So K is the thermal conductivity of the solid. So therefore, if we want to know the total flow across the surfaces, then we have to integrate this over the entire surfaces. All right. So therefore the total flux across S is we will have is given by, let us call the total flux as flux total, suffix total, is equals to we will have surface integral over S K of gradient of u dot n d of S, and if I use Gauss divergence theorem, then it will become volume integral over the divergence of K times gradient of u times d of v. From here to here, we have used Gauss divergence theorem. All right. So this is what we will get from Gauss divergence theorem, and let's call it as equation number 2. Now I will write the rate of change of. So the basically the rate of change of heat energy in the volume V or in the solid is equals to the flux of heat energy across S. So basically the rate of change of heat energy that is given by equation 1 is equals to the total flux or the flux of heat energy, across S, right? Because that will give you the rate of change of heat energy. This equation number 2 will give you the rate of change of heat energy, but we already know from the equation 1 that how much is the total heat energy. So when I say rate of change of total heat energy, it basically means that ddt of this equation number 1, ddt of equation number 1. So if I use equation 1 and equation 2, then let me take a new page. So I'm going to take a new page. So then I will have ddt of volume integral over V. I'm not writing a triple integral. So if I write integral over V, it basically means that the volume integral. And if I write integral over S, then it basically means that surface integral. So here I will get C times rho times U times dV equals to volume integral over V, divergence of K, gradient of U. Let's put a dot here. D of V. We don't need another bracket here. D of V. Now we can use that differentiation under the integral sign. So this ddt will go inside the integral, and it will become del del t. So here I will get del del t of C times rho times U, and I'm going to bring this term on the left hand side. So this will give rho and this one will become divergence of k times gradient of u d of v equals to 0, right? So here what we have is we have c and rho. We have c and rho as let's say constant. So then we can take c and rho out of this partial derivative, and this will give us volume integral over v del t u. I'm putting c and rho here minus divergence of k times gradient of u whole bracket d of v equals to 0. But v was any arbitrary volume. So v was arbitrary. Since v is any arbitrary volume, any arbitrary volume, this basically means that this relation is true for all such volumes chosen in that solid. So if this is true for any arbitrary volume v, that means the integrand must be 0. So if the integrand is 0, then I will have c times rho times del u del t minus divergence of k times gradient of u um, equals to 0. If the conductivity, let's say if the thermal conductivity is constant throughout the body, then in that case I can put this k outside and I will divide both sides by rho. So this will become minus of k divided by 0 divergence of gradient of u equals to 0. I'm calling this as some constant kappa. So if I call that as kappa, then this will become del u del t minus some kappa Laplacian of u equals to 0, where kappa equals to k by 0. And some people also write this equation as del u del t equals to kappa Laplacian of u. And this is the required heat conduction equation that we were talking about. So for a heat conduction problem, this is the required equation that we were talking about. So this equation has many other applications in different branches of physics or applied mathematics. But this is the how to say the basic formulation of that heat conduction problem. Some people also use this equation in case of transport of chemical species in a certain porous medium, or in some in case of some fluid flow. So then in that case, this equation is also termed as a diffusion reaction equation. Now here you only have a diffusion part. So that means if we talk about the reaction part, then in that case, it means there is some kind of sources or sinks that are present in the given flow. Or even in case of your heat conduction problem, this is just like a normal temperature distribution in a solid. But it may happen that you may have some kind of sources or sink that is present in the solid, because of which the temperature distribution will get affected. And then in that case, this equation will transform a little bit. So this is the required equation for heat conduction problem. But in case of sources or sink, this equation will change a little bit, and it will become del u del t minus kappa times Laplacian of u is equals to some f, where f can be a function of u itself, or it can be a function of x and t only. So that depends on the given physical problem. So those things you will come across them, or you will get to learn them when you proceed further in your studies. But it has a very good application. This equation actually connects several problems from the field of applied mathematics. So the situation which I'm talking about is here in this case is connected with either heat conduction problem or a diffusion reaction equation. But people also use this equation in various other contexts. All right, and this is the last equation is the one which is widely used, because this is too basic. So um, if you study an actual application of heat conduction problem or diffusion reaction equation, this equation simply people do not consider because it's too basic. So you more or less start with this type of equation. And there you get to see how your function f will look like, because f is something that contributes some kind of source of sink in your system that makes your problem even more, or your modeling more realistic or close to more physical problem in a way. All right. So this is something which I wanted to show you, where you could see how a partial differential equation is connected with the real world problem. And not only that, once you have these PDs, you can actually solve them using some analytical method, or you can also solve them using numerical method. And the solutions which you get from these PDs will actually tells you how your physical system or how the physical problem which you started originally with is behaving. All right. So these equations play a very important role in mathematical modeling, different branches of engineering and applied mathematics. All right. Now, from here, let us consider this equation. Let me take a new page. I'm going to take a new page now. All right. So in the new page, we know that heat conduction from heat conduction problem, we got the heat equation as del U del T is equals to some kappa times the Laplacian of U. In case of one-dimensional heat flow, one-dimensional problem, your U will become only a function of x and t. Here it is a function of x, y, z, and t. But in case of one-dimensional flow, one-dimensional heat flow, it will become simply a function of x and the time variable t. Then your entire equation will get modified to del U del T equals to some kappa del square U by del x square. That's it. If you have a two-dimensional flow or 2D problem, then in that case, your U will become a function of x, y, and t, or y, z, and t, or x, z, and t. But it will not be a function of three variables. So then in that case, your equation will change to del U del T equals to kappa times del square U by del x square plus del square U by del y square. All right. So this is the one-dimensional flow or one-dimensional problem, and this is the two-dimensional problem. Now, suppose, so now we are going to talk about the Laplace equation. So suppose in case of this two-dimensional flow, this two-dimensional flow, suppose the temperature distribution which you are considering is steady. That means it's not changing with respect to time. So the steady case, basically. That means the time derivative of U is 0, which basically means del U del T is 0. So in case of steady state, that means when there is no change in the temperature with respect to time. So then in that case, your del U del T will become 0. And therefore, from here, let's say we are considering a two-dimensional case. From there, we will have del square U by del x square plus del square U by del y square equals to 0. Now, in 2D, Laplacian is given by this. Some people also write it as delta of U equals to 0. You can write either this or this. It hardly makes any difference. In case of 3D situation, again your del U del T is 0. And what you will have is, in case of 3D, so in 3D, it will become del square U by del x square plus del square U by del y square plus del square U by del z square. You might as well call it as x1, x2, x3, but the equation will not change, which is nothing but your Laplacian of U equals to 0, where Laplacian in 3D is del square by del x square, del square by del y plus del square by del y square plus del square by del z square. In case of 2D, your Laplacian is del square by del x square plus del square by del y square. So it depends whether you are considering a 2D situation or whether you are considering a 3D situation, based on which you will obtain a certain Laplacian. In case of 1D, it is just del square u by del x square. Okay, so that's how we obtain the Laplace equation. So from steady case, you have a heat equation. Now, if you consider a steady case, then in that case, basically you'll end up with Laplace equation. Now, Laplace equation itself has various other varieties, but in general, when we say that Laplace equation, we basically mean nabla square u equals to 0. Okay. If you are considering a 2D situation, then it will have only partial derivative with respect to x and partial derivative with respect to y. If you consider a three-dimensional situation, then it will have partial derivative with respect to x, y, and z. All right. So what we saw is that you are given a certain physical situation. So from there, we can be able to derive certain partial differential equation, which actually depicts those physical problems. That's the same thing we did for when we have the vibration of a stressed string. We obtain the wave equation del square u by del t square equals to c times del square u by del x square. When you have a heat conduction problem, that means when you have some kind of temperature distribution in a solid, then you can be able to obtain heat equation del u del t equals to kappa times del square u by del x square. If you have a steady case, that means when there is no change with respect to when there is no change in temperature with respect to time, then in that case your del u del t will become 0, and what you will end up is basically a Laplace equation. So all these three special type of equation actually will tell you that how beneficial and how useful partial differential equations are. And this is just these three basic equations. I mean, there are very vast variety of equations where partial differential equations which are in some way connected with a physical problem. And you can actually do some numerical simulations, you can do some computations on these partial differential equations to know behavior of that physical problem or of that real world problem. And in it itself, it's a very how to say amazing tool that gives you or that acts as a bridge between the physical problem and the mathematical understanding of those problems. So PDE gives you that bridge, or it connects our mathematical analysis and our understanding with the physical problem. All right. So that's that. Now that we know how these equations look like, when we actually try to solve a physical problem, there are two things together with these equations we have to take care of. So from the theory of ordinary differential equation, you might be aware that if you have a second order ordinary differential equation and when you solve it, then you get basically two arbitrary constants. Now, in order to determine those arbitrary constants, you were given some kind of initial condition or some kind of boundary condition, things like that, so that you will get the unique solution. So here in this case, in case of these three special type of PDEs, when we are trying to solve them, um, we will you will see in the next one or two class that how we are solving them. So there is a method called separation of variable that we are going to implement, and with the help of which we will solve these PDEs. But the thing is, when you are trying to solve them, you also need some kind of initial conditions on these PDEs and some kind of boundary conditions. All right. So it will not be always straightforward to get the unique solution. In order to get the solution, you always need to impose some kind of initial conditions, some kind of boundary conditions on these PDEs. Now, how you implement, how you impose those conditions, that also plays a very important role. So, for example, let's start with our wave equation, and we will see in what situation, what kind of boundary condition we need to impose. All right. So I'm going to start a new page now. All right. So let's start with a new page. So our given wave equation, is let's say del square u by um, del square u by del t square equals to c times del square u by del x square. All right. We are talking about wave equation. So if you consider an infinite string, it may happen that the string is infinite. That means minus infinity less than x less than infinity and t is positive. So then in this case, there is something called D'Alembert solution that we have to implement here. So in this case, we really cannot impose any kind of boundary condition here, because at u infinity, at u minus infinity comma t and u infinity comma t, um, for all t positive, we just don't know what kind of boundary condition that we have to implement, because at x equals to minus infinity, it will be difficult to how to say impose any type of boundary condition on this function u. All right. So here in this case, at u is equals to at u at x equals to minus infinity and at x equals to infinity, we are basically not implementing any kind of boundary condition. Now what we can do is that we can always impose some kind of initial condition. So let's say we are saying u at x comma 0 equals to some f of x, and ut x comma 0 equals to some g of x for x in here. So here what we can do, we can impose some initial condition, but we are not imposing any kind of boundary condition. Now, if I change the situation to a semi-infinite string, semi-infinite string, then in that case, this same problem will reduce to del u by del t square c times del square u by del x square, where 0 less than x less than infinity and t is positive. Now here you can see the string has now become semi-infinite. I mean, that means instead of going from minus infinity to plus infinity, now it is going from 0 to infinity. So now one end is finite. So we know that one end is attached at 0. So the end which is actually attached at 0, that's like one boundary point. And the string which is attached at 0, there we are not experiencing any vibration. So there your u will actually be 0, right? Just after 0, it starts to vibrate, or it starts to do those vibration. So there at x greater than 0, it has a vibration, but exactly at x equals to 0, since the string is attached, we are saying that u is 0. So our first boundary condition that we can implement is the boundary condition is u at 0 comma t equals to 0 for all t, exactly at x equals to 0. But at x greater than 0, we don't know. All right. So now we can implement some initial condition. And the initial conditions are, we are saying ut, initial condition means, let's not write t first, let's write u first. So u x comma 0 equals to some function f of x for every x, we will write that, and ut x comma 0 equals to some g of x for every x greater than 0. You can see that t is 0. So when t is 0, that's when we call it as initial condition. Initial condition usually mean that at initial time, and usually the initial time is considered as t equals to 0. So that's why we have substituted t equals to 0. So u x comma 0 basically mean u at initial time t equals to 0. So that is u x comma 0 equals to f of x, and ut x comma 0 equals to g of x. So these two will be considered as initial condition, whereas this one will be considered as boundary condition. All right. Now, and another interesting fact is that you have finite string. Let's say instead of semi-infinite, you now have finite string. So obviously the equation will remain del square u by del t square equals to c times del square u by del x square. And I'm saying that the length of this string is 0 less than x less than L and t is positive. So obviously in this case, your string is attached to two finite points, so 0 and L. So obviously at 0, there is no vibration. So u at 0 comma t will be 0. And at L, the another end where the string is attached, there also there is no vibration. The vibration is happening in between. So there also I will take u L t comma 0, u L comma t equals to 0, right? So here I can have two boundary conditions. So the boundary conditions are, I can have u0t equals to 0 and ult, the two ends for all t positive. And I can also have some initial conditions. So initial condition will remain as before, u of x0 equals to f of x and ut of x comma 0 equals to g of x for every x positive. So now in this case, in case of finite string, I am afford to have two boundary conditions and two initial conditions. With the help of this, we can be able to write down the solution via separation of variable method that we are going to learn in the next one or two classes. All right. So you see how we can implement the initial condition or boundary conditions. In case of infinite string, we really didn't have any boundary condition. We only had the initial condition. But in case of semi-infinite string, we had one boundary condition and two initial condition. Whereas in case of finite string, we can have two boundary conditions and two initial conditions. All right. So depending on the physical situation or the context in which you are working, you can have these type of boundary conditions. Alternatively, depending on the situation. All right. Now, I'm going to talk to you about heat conduction problem. So let me just look at my lecture note where I have this heat conduction problem. Where is that? Yes. So that was so here I showed you how to prescribe boundary condition and initial condition on a wave equation problem. Now, let me start a new page. Save, and then I will start a new page. All right. So let's consider heat equation. Heat equation. So we know that heat equation is given by del u del t equals to c times del square u by del x square. Suppose the length of the rod is, or length of the solid is L and T is positive. All right. So here in this case, you have a solid bar and of length 0 to L. So suppose I can write it like this. X-axis, this one is U, xt, and suppose zero to L. All right. So here I can prescribe the boundary condition based on the requirement. All right. So let's say for the time being, I'm saying this end of the rod and this end of the rod, they are both at 0 degree. That means there is really no heat or heat sources that are placed at the end the x equals to 0 and at the end x equals to L. So then in that case, I will say u0t is equals to 0 and ult is also equals to 0 for all t positive. So this is how I'm prescribing the boundary condition for this heat conduction problem. And I can have initial condition as u of x 0 equals to f of x for every x between 0 to L. You can write for every x between 0 to L. So like that. You might as well prescribe the boundary condition. Let's say this one was this problem 1, sub problem 2. So you might as well prescribe the boundary condition as, so instead of kappa, I'm calling it as C. I can prescribe the boundary condition that I have placed some kind of heat source at the end 0, sorry, at the end origin, which is of 100 degrees centigrade. And at another end, I'm saying that the temperature during the temperature flow through this rod, the temperature at the other end is becoming 0. So I might prescribe it as U0T equals to 100 degree and ULT. You can have L as 1 or 2 units. So 1 meter or 2 meter, something like that. And this one is 0. So for all t positive, and ux comma 0 equals to f of x for every x in 0 comma L. All right. You might as well use some kind of function also. So depending upon what kind of situation that we are dealing with, we can describe such kind of boundary condition at either end of the rod, and we can also have a specified initial condition. So fx could be, I don't know, sine x or x times 1 minus x, things like that. And then you have a complete boundary value problem where your one end of the boundary value is 100, another end of the boundary value is 0, and ux comma 0 equals to 50x, let's say. Then you can solve this diffusion reaction, this heat conduction problem. And of course, we have to take the length of the rod as finite in this case. And using the method of separation of variable, you can be able to find a solution of this problem. All right. For the elliptic equation also, let me just have a look at my note. I will tell you what kind of condition you can prescribe on elliptic equation also. So Laplace equation is basically an elliptic equation, and in case of Laplace equation, let me just go back to let me start a new page. So we know that now we are going to talk about boundary condition or initial condition, whether we can impose on Laplace equation. So as obvious, we have Laplace equation as the Laplace of u or nabla square u equals to 0. So nabla square u, in case of two-dimensional geometry, it will become del square u by del x square plus del square u by del y square equals to 0. So suppose we are in a situation, so of course this is a steady state temperature distribution or steady state case. So suppose we are in a situation of this type. So here we have x equals to a, and here we have y equals to b. So our 0 lesser equal to x lesser equal to a, and 0 lesser equal to y lesser equal to b. That's the given given domain. So here is somewhere we have our Laplacian of u equals to 0. So that's where we have the, if I can be able to draw with the pencil. So this is where we have the Laplacian of u equals to 0 value. That's the region where we are considering Laplacian of u equals to 0. All right. Now we can prescribe the boundary condition in this fashion. I'm saying that at this boundary, I have ux comma 0 equals to f1 of x. Now on this boundary, y is equals to b. So I'm saying ux comma b is equals to f2 of x. At this boundary, we have x at 0. So I'm saying u0y equals to some g1 of y. And at this boundary, I have x equals to a. So uay equals to some g2 of y. So I was able to prescribe four boundary conditions. How? ux0 equals to f1 of x, and uxb equals to f2 of x, where 0 less than x less than a, and u0y equals to g1 of y, and uay equals to g2 of y, where 0 less than y less than. So this is one way that we can prescribe the boundary conditions on a Laplace equation, on a elliptic equation of this type. So here, obviously, Laplace equation, what I told you before, connects to the steady case or steady state temperature distribution. So we are saying that inside this rod of length a and height b, our Laplacian of u is 0, and at the boundary of this, we are prescribing the boundary conditions as ux0 equals to f1 f x, uxb equals to f2 of x, u0y equals to g1 of y, and uay equals to g2 of y. And using these boundary conditions, we can be able to solve this Laplace equation, um, where the solution will be given by method of separation of variables. All right. Now that we are talking about solution, first of all, we also have to make sure that what kind of solution we are talking about. So solution of wave equation or heat equation or Laplace equation or Laplace equation. Okay, wave equation or heat equation or Laplace equation, either one of them. Let's say we want to talk about the solution. Let's start with the Laplace equation. So Laplace of u equals to 0. Obviously, from here, it is apparent right away that if I substitute u equals to 0, then this Laplacian of u is always 0. We don't have to verify. Or if you substitute u equals to 0 in your wave equation, then your wave equation will always be satisfied. Or if you substitute u equals to 0 in your heat equation, in that case also it is always satisfied. But the thing is, u equals to 0 will not give us any significant information, because u is equals to 0 basically says that in case of heat conduction problem, it basically says that the temperature is 0 throughout the material body. But that's not the case. I mean, it may happen that there is some kind of temperature distribution. It's just that we have considered u is equals to 0. So u is equals to 0 is not an ideal choice of the solution. So therefore, we cannot consider u is equals to 0. That means we should always try to find non-trivial solution. Non-trivial solution. That means solution which is not equals to 0. That is, we are looking for the solution which are not equals to 0. Because u is equals to 0 will always be satisfied, but it doesn't give any information. So we will not be interested to find a trivial solution at all. In case of method of separation of variable, we will run into the situation which lead to the trivial solution, but we will not consider those situations. Rather, we will make different choices on the arbitrary constant that are involved in the solution of the PDE, such that the solution end up being non-trivial solution. So having a trivial solution is not an ideal case, and therefore we will always look for non-trivial solution. Another example, you might say that let us consider uxy equals to x plus y. So something like that, more of a linear solution case. So again, these kind of solution, of course, it is not a trivial solution, but it's also very not an ideal choice of the solution, because if you substitute here, it will satisfy your Laplace equation, but you also have some boundary condition. It may happen that this type of solution is not satisfying your boundary condition. That's first thing. And the second thing is that this is too simple to choose actually. So we have to choose solution, or we have to find solution which are not trivial and which also doesn't look straightforward like this one. So We have to choose the solution which obviously satisfies, or we have to find the solution which satisfies the given partial differential equation together with the boundary condition. So we always have to use the information, all the information that is given to us. The PD itself, the physical context in which we have considered the PD, which will be apparent from the boundary condition. So that means that with the help of boundary condition, we'll be able to determine a non-trivial solution. All right. And all those things we will get to learn in our next class. Well, next class I will talk about Fourier series, but class next to next class, you will get to learn about probably separation of variable method. There you'll be able to see how the information on from the boundary conditions is useful, or it will be implemented to determine the non-trivial solution. All right. So I try to give you the modeling technique or the motivation behind these special type of PDs, how they come from the physical problem. And I also tried to show you what kind of boundary conditions that you can impose on these PDs based on your physical situation. So you have a certain physical situation that will give you an idea that what kind of boundary conditions that you have to choose. And then you supplement your PD with those boundary conditions the way I showed you, and then you solve it. And I also gave you an idea that we should not be considering a trivial solution. Rather, we should always be interested, or we should always look for non-trivial solutions. So these are the summary of today's class. And in the next class, I will talk about Fourier series in short, because Fourier series itself is a very big topic and we cannot be able to cover it in one class. So therefore, I will just give you a slight introduction of Fourier series and how it is connected with the separation of variable method that you will see when you learn the separation of variable method. But in the next class, in the next class, we will just learn some techniques or some introduction, and maybe we will solve one or two examples from Fourier series. So that is all from today's class, and I will see you in the next class. So bye from me now.